What we're talking about today is going to be ultrasonic inspection of electrical gear. This is going to be presented by Joe Gierlach with the TEGG Corporation, and I'm your host today, Gary Moore with UE Systems. We're going to take you some of this stuff, and hopefully we can give you some real useful information that you're going to be able to use out in the field in your daily job. So a little bit about UE Systems. UE Systems, we were founded back in 1973. We've got now 35 years experience plus, I guess, in the ultrasonic field. We've got a very large global footprint we've got regional offices around the world, USA, Canada, Mexico, Europe. We've got a whole group of independent distributors worldwide, some 200 plus. We haven't bothered to count them lately, but there's quite a crew of them. So we have a large footprint around the world. That's enough about me. Joe, do I have you on the line here with us? What I wanted to do here was I wanted to welcome Joe Gierlach and bring him on board with us here, and we'll turn this over to Joe. Joe, are you with us?
I am. Good afternoon, Gary.
Good. Well, welcome, Joe. It's great to have you. Joe's been a good friend for UE Systems and the ultrasonic technology as a whole for quite a length of time. And with that, Joe, I'm going to give it over to you. I'll let you take it from here, and you can tell us what you do.
All right. Thanks, Gary.
Now, what I'm going to do at the same time, you're still seeing this, Joe? I'm turning this over to you, and the people that are on with this are now going to actually see your screen.
Okay, great. That should be up right now.
Yes, it is, Joe.
All right, well, good afternoon, everybody. As Gary said, my name is Joe Gierlach, and I'm with TEGG Corporation out of Pittsburgh, Pennsylvania. It's a privilege to be here today. Been good friends professionally and somewhat on a personal level with the folks at UE Systems, and we've got a really good working relationship, and have done a lot of neat things together over the years here. I've presented at a couple of the seminars or the Ultrasound World Conferences in the years gone by here, and this seemed to be a popular subject with electrical inspections. As everybody may imagine, the electrical inspections are really only a small slice of the pie that the ultraprobe is capable of, but it's a very important part of what we do, and that's what I want to talk about today. TEGG Corporation has been around since 1992 when it was incorporated in Pittsburgh. At our corporate office in Pittsburgh, we have 37 core employees that handle a network that's now international of over 160 independently owned electrical contractors in 21 different countries. We have most of North America covered, Bermuda, Australia, all of the United Kingdom, Ireland, and slowly but surely we've been moving into Western and Eastern Europe, and that grows as we speak today. TEGG and UE Systems have been partners for a long time, and when I joined the company 7 or 8 years ago in Pittsburgh, Doug Wagen approached me to kind of reinvigorate the relationship, and we've been building on that ever since, and it's worked out very well. Ultrasonic testing is a very critical step in our electrical preventive maintenance and predictive maintenance process, and it's never separated with some other more popular technologies, maybe such as infrared thermography and using imaging. It complements that very well in many ways, as everybody probably knows, in that there are a lot of things that the infrared camera has limitations on, but the ultrasonic probe makes up for in many ways. So we view it as a very important instrument in our bag of tools, and we are never without it. And there have been a lot of good finds out there. The experience has proven that the technology can be used effectively not only on high voltage systems and medium voltage systems, but low voltage as well. And I'm going to talk about some examples of that today. If there's anybody in the listening audience that has electrical needs or needs consultation or support on the ultrasonic probe or any other technologies, feel free to visit our website at TEGG.com, and you can find the local TEGG contractor in your area, and they can help you in any way you need. about myself a little bit. My background is maintenance electrical. I've spent the better part of 20 years working in this field. Started out in the U.S. Air Force back in the mid-'80s, and that was a very good experience with a lot of lessons that stick with me to this day. After I separated from the Air Force, I went to work for a shipyard in the Northeast up in Bath, Maine called Bath Iron Works. And that was an interesting experience for a little over a year, building ships for the U.S. Navy. After the birth of my son, I decided I was going to move south where it was warmer and relocated to Central Florida in the Lakeland, Florida area where I lived for 10 years. And in that time, I worked for the phosphate and chemical fertilizer industry. And the unique part about that experience was the chemical plants all had cogeneration. A lot of waste heat, if you will, installed boilers, put the cogens in, made all the electricity we used, and sold the rest back to the utility company. So I like to say I cut my proverbial teeth in Florida with all the good experiences. When you work from the generation side of things through transmission, distribution, all the way down to process and loop control, you get exposed to a lot of things, and I've been very fortunate to be around many people who know a lot of things, and that served me very well to this day. After 10 years of the heat and humidity in Florida, I decided I'd come back to Pennsylvania in the Pittsburgh area, and back in the mid to late 90s, I relocated and went to work for a steel mill, making steel pipe and conduit. It was a great experience, although it was a very dirty, nasty, noisy, dangerous place to work. Learned a lot more about a lot of different things. Very cyclical industry, so layoffs in a seniority-based shop. The junior man doesn't work. That was me. I did not like that, so I decided to change jobs and go to work for a titanium company in Niles, Ohio, and spent 2 years there where they make raw materials for military applications and commercial aerospace, medical parts, things of that nature, with a lot of work for years to come, and contracts with Boeing and Airbus in the U.S. Air Force, and that was very good until September 11th terrorist attacks happened, where Boeing and Airbus canceled their orders and the military realigned their priorities. So I decided to put my resume out on the internet. It was found by the recruiter TEGG Corporation, called me in for an interview, and the rest is history. So I've spent a little over 7 years with TEGG, and it's been a great experience. In that time, I have taken courses. I'm currently a level 3 infrared thermographer. I possess a level 2 airborne ultrasonic certification, and recently completed my 10 and 30-hour OSHA instructor class as an authorized instructor, working my way toward a professional certificate in occupational safety and health. I got 4 people that work for me in my department, and we support the network as we go. So that's a little bit about me, and we'll go ahead and get right into this on the topics that I'd like to discuss in this hour. I've entitled this "What You Can't Hear Can't Hurt You," because as everybody knows, the ultraprobe works at frequencies that are inaudible to the human ear. And there are a lot of things that occur in electrical distribution system components that create ultrasonic emissions that, if otherwise undetected, could result in unscheduled outages, failures, or catastrophic failures even. So if you cannot detect these early and address them on your terms, it can truly have dire consequences. So I want to talk about some of these anomalies that are found in electrical equipment and the different techniques that are used to detect those anomalies, as far as the airborne trisonic scanning module, as well as the stethoscope probe or the contact module, and where they have a place utilizing this technology with electrical maintenance. I'm going to touch on the frequency signatures of the common anomalies in electrical. And what I mean by that is we believe every anomaly, and they can be narrowed down to 5 or 6 in electrical that can be detrimental, have what I call a spectral footprint. There is a unique pattern that you look for using the spectralizer software with respect to frequency peaks and noise content in between the frequency peaks. The same applies to the time domain analysis, where you're looking at excursions and amplitude over a time period of the recording. And I'll get into that a little more with the anomalies as we go along here. The problems that occur have effects on electrical insulators that can compromise the integrity of doing their job. And detecting them early can help preserve or at least save the insulating systems that are in the system. And then finally, a little bit about severity classifications. And it's a question I get all the time in my network. How severe is this issue? And it may not be what you expect as far as what our experiences have been, but I will share with you what we have come up with. Deterioration or breakdown of insulating material comes in several forms. And the bad thing about it is when it starts to deteriorate, it loses its ability to maintain or contain the potential within there. And it prevents it from performing properly. When this occurs and the insulation breaks down, you get discharges along those insulators or through them that are seeking a path to ground. And as these discharges occur, it creates the high-frequency emissions that we're detecting with the ultrasonic probe. So the most common ones found in electrical are arcing, tracking, and in high-voltage systems over 1,000 volts, corona. And in the images you see on the screen right now, that would be visualized examples of each of those anomalies. On the left is a 20-amp circuit breaker that was arcing on the line side connection. Unfortunately, did not go to another phase. The middle image shows an I-line square D panel where there was a bunch of tracking occurring on some of the circuit breakers, and the telltale sign there was the carbon trails that were left on the bus and the bakelite material, the insulating material there. Finally, on the right, you have some high-voltage terminations where corona had been taking place for whatever reason and became destructive in nature with the watermarks and trees and spidering trails, which are a telltale sign of that. Detection of these come two different ways, as most of you are probably familiar with. The airborne module, which is optimized for 40 kilohertz, and we choose to use it religiously with the rubber focusing cone. There's two reasons for that. Narrowing the field of view makes it much easier to isolate down the source of the emission, and since we're dealing with energized electrical systems, rubber's a good insulator, so it certainly provides a barrier or a shield between the technician that's using the instrument and the component that he may be scanning at that time. The stethoscope module, as you know, it becomes a sound wave guide, and it's a method of channeling the sound waves into the instrument when there's a medium in between where the source of the emission may be and the instrument itself. Some examples of that may be multi-case circuit breakers, enclosed bus duct, liquid-filled transformers, anything where there's a medium in between the instrument and where the emission may be occurring. The optimal frequency there, as you know, is 20 to 30 kilohertz, and we typically begin at 25 kilohertz and tune the instrument from there as we identify any types of anomalies. Just reviewing the definition of some of these things we're looking for. Arcing is the first one we talk about. And if you wanted to describe what arcing is, you have a full intensity discharge that erupts, and then it goes to full silent. And there's not a clearly defined pattern with respect to time when this may occur. It depends on how severe the situation may be. You can associate that with an arc welder. When you strike an arc, that's arcing in its purest form. But we have these same types of situations occurring inside electrical equipment at frequencies that you may or may not hear. And when you do identify arcing in its purest form, as you may have been told in the past, failure is occurring right before your very eyes. It needs attention immediately. And I'm going to attempt to play this sound file just to review it, and if it doesn't come through, as Gary said, we'll put it up on the website. But we'll try it here. If you can hear it, you're familiar with the sound. If not, we'll put it up. So I don't know if that played, but
Didn't get that, Joe.
pardon me?
I did not hear it, but we can see it. Okay.
Okay. It's a sample file that comes with your probe, and everybody is probably familiar with it. When you take a sound like that, from our standpoint, what we feel we need to do is visualize that sound to our end user customers. In other words, paint a picture of what that sound would look like in a manner that's explainable when you identify them. Looking at the frequency and time domains on this slide right here shows you what does arcing look like from the frequency standpoint on the left and from the time domain on the right. If you look at frequency, and assuming we are on 60 hertz systems, we're going to put a 60 hertz harmonic cursor on the spectralizer. And what we traditionally see is the first couple of 60 hertz harmonics. And what a harmonic is, for those not familiar, is a multiple of the base frequency. So if you're on a 60 hertz system, the second harmonic would be 120 hertz, the third harmonic would be 180 hertz, and so on down the line. We traditionally see 2 or 3 of these harmonics as what's called false frequencies, or spikes in the frequency spectrum, and in between each of those peaks there, or 60 hertz cursors, there's a lot of activity going on, or frequency content. That's indicative with an electrical type problem where you have a lot of activity, for lack of better words, or high amount of frequency content. This particular domain here on the frequency can be confused with other electrical problems that to us and orally sound very different. So to use just the FFT as a standalone tool would be a mistake, in my opinion. When you combine that with the time domain analysis and looking on the right screen capture, with electrical components, in most cases, one would expect to hear nothing. There's few exceptions to that, but you would have a broadband or a narrow band of white noise across the time domain if it's functioning properly. And the exceptions to that may be rotating equipment, bearings, transformers, motor contactors, things of that nature. But when we're dealing with circuit breakers and disconnects, switchgear, distribution boards, traditionally they should be totally silent, and you would see nothing in the time domain. It would be just a band of noise. In the right-hand side for the arcing, though, we see that band of noise throughout the middle all the way across the recording, but there's other elements imposed on top of that, and specifically, I call them excursions. And if you look at where these excursions occur throughout the recording, those would be the points in time where the discharges are occurring. So moving left to right, you see we're silent for a portion, and then there's a discharge. Goes to full intensity. Then it's totally quiet again, and we have several more discharges across the length of that 6 or 10 second recording there. To explain this in conjunction with the recording to a customer makes it far easier to understand. And when you compare this to samples that you know to be true, it's easy to make a good call. So those would be visualizing the arcing anomaly that we're talking about here. And the next slide kind of explains what I said, because I'm very bad at switching slides, so I'll have to apologize. But the first couple of harmonics in the frequency, a lot of frequency content in between those harmonics, and then the excursions do not have a distinguishable pattern across the time domain, but you can see and visualize the discharges back to full silent and when the discharge occurs once again. If you want to associate this with an electrical sine wave, I was over in Australia a couple years ago with Mark Goodman from UE Systems, and he kind of put this together relative to the electrical sine wave, which I thought was a really good way of describing where these discharges are occurring on that cycle. And if you look, there's not a real distinct pattern or respective to time when those discharges occur. With arcing, it could be anywhere on the sine wave, which is why there's no pattern on both the frequency domain or the time domain. So you could have a discharge anywhere on there. It could be visualized in a very similar fashion as we saw on the previous slide. There's occasions where a 5 or a 10-second recording may not be quite enough when it comes to arcing. In its very early stages, the arcing may not be frequent in its discharges, but it still could be present. And this is at the very early stages where insulation systems begin to fail. We'll put it up. This is a transformer over in Brisbane, Australia. And we were using the contact module on the high voltage side of the transformer, which is an 11 kV primary down to a 400 volt secondary. And we made a 30-second recording. And at 1.5 seconds and 9.5 seconds of the recording, if you've ever used the contact module and you move the instrument, you may hear something in the probe. And it sounded just like that, but being very still, we knew that we had not moved the probe, and there were 2 discharges that occurred over a 30-second recording. I'm going to pull up here the frequency and time domain view of that particular recording. And if you look right here, in the red, we have a known sample of arcing, as we saw a few slides ago. And we overlay the recording that we made on the transformer with that known sample. And although it is not identical in nature, we look for the similarities, or as I called them earlier, the footprints. I'm looking for the first few harmonic frequencies that may occur. Because we're in Australia, the operating systems there are 50 hertz. So I got the harmonic cursor set to 50 hertz. And we can see we have some characteristic similarities here. There is several 50 hertz harmonics in the beginning of the spectrum, and very telling is the amount of frequency content or noise that appears in between each one of those harmonics. It is very busy, for lack of better words. So that's a tip-off that we want to look at something else, in particular the time domain. And as we look over there, we have that characteristic broadband of white noise through the entire length of the recording. That should be normal for a transformer in this case. But you see 2 distinct excursions there, and I'll switch to the next slide, that coincide what was heard and recorded within the instrument. Based on this analysis right here, we recommended the customer that they do a few other things because we knew we had early stages of insulation breakdown within this liquid-filled transformer. And they're not as easily replaced or readily available today as they used to be in the past. So you want to catch items like this early. This transformer was at a college campus, and it was in a high-activity area. So the customer did not want to see the transformer fail, and we came up with an action plan to monitor this. Would I suggest shutting the transformer down based on this find and replacing it? No, I would not. There are some other steps that we could take because it does indicate breakdown internally. Now,
Joe, can I interrupt you one moment here?
Yes,
I have one
please.
question and it's actually a great question here. I didn't see who, but it says, does this technology provide indications of a problem before we would see a change with IR? And so can you just give us a little bit of insight how you see this working with IR instead of IR?
Yes, actually, I was just getting ready to tie that together, so it is a great timing on the question. I thank the person who put that in. If you look at this screen right here, traditionally, and I'm going to narrow this down to a transformer, a liquid-filled transformer. You have a medium inside the transformer. The area of interest is going to be the windings, the winding insulation, and the terminations within that particular unit. The insulating oil is a cooling medium, and if you have anomalies like arcing occurring, there is a high volume of thermal energy or heat that is produced with the arcs. The challenge with infrared becomes you need to change the temperature of that insulating oil dramatically before the infrared camera would be able to determine that this was occurring inside. The slide I have up currently shows what a liquid-filled transformer should look like to the infrared camera, meaning we have a very uniform and consistent pattern all the way across the area of the vessel. When infrared sees an issue like this, particularly on a liquid-filled transformer, it's typically too late. So to answer the question most specifically, the ultraprobe in many cases can provide earlier indication of problems within components that you cannot get a line of sight to than the infrared camera will. So if you do see it with the infrared camera, it's probably in the latter stages of failure, and you may not be able to act soon enough. This is the type of image we would like to see, even if arcing is going on, be it the time domain I showed you a moment ago, or it could be a continual, more frequent arc within this type of unit. It would be quite some time before it would raise the temperature of the insulating oil enough to where the infrared camera would be able to see it. And I hope that answers the question. But based on the time domain analysis, we know there are discharges occurring within. We need to take some remedial steps to monitor that unit and see if it gets worse as time goes by. Now, the next step in this particular example, we suggested procuring 2 oil samples, what's called a jar sample for screening of the insulating fluid itself, as well as a syringe sample to do what's called a dissolved gas in oil analysis. When you have tracking or arcing or corona, be it nuisance or destructive within an oil-filled component, there are certain combustible gases that are released within the oil. And with laboratory analysis, those can be identified to confirm the findings of things like the ultraprobe would indicate. And that was certainly a next step in this particular find. And the customer began to trend the dissolved gas in oil analysis results over the next 6 to 12 months. And with an increase in those values, things like acetylene and methane, the combustible gases, that would indicate that the unit is in fact deteriorating and back up what we find, or what we had found with the ultraprobe, which was the early stages of the arcing that was taking place inside. The thing about electrical equipment, when it begins to fail, rarely does it change course and repair itself. And the earlier you can detect these types of anomalies, the quicker you can get corrective actions in place, and that reduces the cost of maintaining it as well as repairing it. So the trending is a very important thing. As I said, the ultraprobe is a complement to many other technologies, and you don't want to rely on just one technology to define your course of action. Occasionally, you do not even need the ultraprobe to determine that arcing is taking place. And one example of that everybody should be familiar with is lightning. That is arcing in its purest form. When you have these discharges in the atmosphere, it's very loud with the thunder, but it's bright, it develops a lot of heat, and it certainly can be heard audibly with the human ear. With respect to the oil sample, although we're very interested in the combustible gases that show up in these samples, occasionally when you do use the infrared camera, you don't even need to worry about taking an oil sample. On this slide right here, this is an extreme case of where infrared would tell you there's something wrong, even in the absence of ultrasonic emissions. This is a liquid-filled transformer that is 2,500 kVA in New Jersey, and sent to me by one of my technicians. You should never, under any circumstances, be able to discern with this type of detail the windings inside of that unit. And the problem with this unit was there was no insulating oil. So the efficiency was out the window. The life expectancy of the unit was dramatically reduced. And this is a perfect example of what you don't want to see on a liquid-filled transformer. Now, was there ultrasonic emissions on this one? Not yet. But without the insulating oil, as loads are added, it will put stresses on the insulating material, ultimately break it down, and odds are you will have ultrasonic emissions down the road.
Joe, can I interrupt you with another question here? I've got one that says, can oil sampling alone catch the problem of arcing inside the transformer?
I would say that it will catch it later on. There needs to be a longer period of the arcing taking place to release these gases depending on the amount of oil that's within the vessel. Typically when we're dealing with liquid-filled transformers, we're talking about vessels that have a minimum of 500 to 700 gallons of oil in it. So to detect the combustible gases in there, the arcing will have had to take place for a longer period of time than we'd like to see. It's a great way to verify, particularly in the early stages, do we in fact have this occurring inside. There's combinations of gases that are very specific to arcing, as well as tracking, and as well as corona.
Thanks, Joe.
You're welcome. Whatever the case may be, the biggest thing is we want to prevent damage and destruction to the equipment. I've always found that it is far easier to deal with equipment problems on terms that I dictate as opposed to letting the equipment dictate that to me. So damage can occur in many different forms. These are arcs that have occurred on different equipment here. You can see the discoloration of the insulation on the left-hand side there for a dry type unit not contained in oil, as well as an aircraft connection here where a hole is blown in the tube. And ultimately, we do not want to see any type of destruction that traditionally is not limited to the component of failure alone. If there's a catastrophic failure in a piece of equipment, the upstream and downstream components can be at risk of sustaining damage or destruction as well. And that's the name of the game, is we want to prevent this from happening. Arcing is certainly an anomaly that can lead to this type of destruction. So the earlier you find it, the more likely you are to prevent a failure. Moving on to tracking, it's very similar to arcing in nature. What I mean by that, tracking gets referred to as baby arcing because there are discharges of electricity that occur along insulating materials that aren't supposed to be conductors. And when these discharges occur, there's usually carbon trails that are left behind as visual evidence. But using the ultra probe as a safety mechanism or a first line of defense, we wouldn't traditionally have a line of sight to what we are interested in. So the carbon trails may not be visible. The characteristic sound from an aural standpoint of tracking, as you may have heard on your sound files, would be a buzzing sound with a snap, crackle, pop superimposed on top of that as these discharges occur. I equate it to Rice Krispies. So when you hear that, it can be very alarming. Does infrared see tracking? The answer to that is no. With discharges along insulators, what's absent is current flow. And for infrared to be effective, you have to have thermal effects and temperature differences. And in electrical systems, that means current flow. So with tracking, you do not have that current flow, although the discharges are seeking a path to ground. They have not found that yet. So you will not see tracking with infrared. If you're fortunate, you will see the carbon trails that are left behind by these discharges, but in most cases, we're using the ultra probe prior to even opening equipment and would not have that opportunity to see those. If you look at tracking in the frequency and time domain, on the left-hand side here, it's very interesting because I like to say that arcing and tracking are almost twins in the frequency domain. And what I mean by twins is that the characteristic footprints are nearly identical. We have the first couple of fault frequencies on the harmonics, depending on which base frequency you're working with. and a lot of activity or frequency noise occurring in between those harmonics. If you were to use just the FFT tool, you could mistakenly call arcing tracking, or you could call tracking arcing. They're that similar based on our experiences. Where the major difference is in the time domain, which is why I believe you must use both these tools every time when you have a suspected problem. If you recall on the arcing, we had the broad band of white noise, and we had the full intensity discharges with no real rhyme or reason that occurred throughout the recording. On the tracking, we have the same broad band of white noise, but we have many excursions here that are more frequent in this case than the arcing was. The key thing here is we have the multiple excursions all the way across there, but you have varying levels of intensity or amplitude. This is one of the things I look for tracking, is no consistency in the amplitude on the excursions. Another thing I have found is the more tightly compact that these excursions become. In other words, a higher rate of frequency that the discharges are occurring, the more severe the tracking is becoming. So that's one of the key things I focus in on here with tracking, is looking for those excursions that are not symmetrical in the amplitude and become more tightly compact, suggesting that the discharges are occurring at a higher rate or a faster rate. On the sine wave, again, similar to the arcing, you get the asymmetrical patterns there and the lack of consistency in the timing, because the discharges could occur at any point on the sine wave. So that helps correlate what we're seeing in the time domain as far as what type of anomaly we may be dealing with. Now, those amplitudes and the compact nature of the excursions are going to change even on known samples depending on the severity of the tracking. And the reality is, ultimately, tracking will degrade and turn into full-blown arcing, and that's typically right before a failure. So we want to find this early. There's another sound file here just from a molded case circuit breaker that we recorded over in the UK. And you can see that here on this slide. I have both the visual image and the digital image of that particular device. And it's only a 60 amp circuit breaker. But on the sound file, it was very clear that we had the traditional buzzing sound with the snap, crackle, pop. And when analyzed, we could see that pattern, particularly in the time domain, that had the broadband white noise, the asymmetrical excursions, and the varying amplitudes and spacing throughout the recording. Interestingly, and as I noted before, you do not see that on the infrared. You see load-related heat here on the right side with the infrared images, but there's nothing to suggest that something may be occurring inside this device. So it's another example of how ultrasound has definitely helped identify something far more early than infrared could, because we don't have excessive current flow resulting from the tracking to the point where the infrared camera could see it. In the frequency and time domain, on this slide, I have the recording shown with the red trace and a known sample of tracking in the white trace. Now, the largest difference here is I still have the first few fault frequencies and a lot of frequency content in both recordings. The amplitudes of the frequency faults on the known sample are somewhat higher because the circuit breaker we found was just light tracking. It was early stages. So we didn't have as high of an amplitude on those fault frequencies. The time domain, we have a larger band of white noise here only because it was magnified somewhat. But looking at the excursions, you can see that they are more tightly compact, and there's no symmetry to them as far as the amplitude throughout the recording. It varies all the way across, which is a spectral footprint of the tracking anomaly. And that's an 8.9 second recording, as it says right there, it still has the similarities from the known samples that give us the confidence to say this is what's going on within that device. So they're not as pronounced or large as the known sample, but the pattern that it presents certainly indicates the presence of tracking within that device. The visual evidence that I mentioned related to the tracking anomaly comes in the form of carbon. And I have 3 images here that show the byproduct of tracking occurring. On the left-hand side was a 3,000 amp bolt-in circuit breaker sent to us by one of our customers in Mississippi. And they identified this issue and was able to isolate it down to the line side of the B phase on the breaker as the highest intensity level. And I get a lot of questions about decibel level. And although decibel level is a very important parameter, when it comes to electrical, it cannot be used as a gauge for severity. For my purposes with arcing, tracking, and corona, the dB level increasing only represents how close I am to the source of that emission. It has nothing to do with severity in most cases. So the higher the dB level, the closer I am to the source. We use that as a technique to isolate down where the origin of the emission is coming from. The problem with carbon trails here is it's a very good conductor. Motor brushes and things of that nature are made from carbon. They conduct electricity very well. If the buildup gets to the extent where it can bridge the path to ground, you have a flashover. And this is what we want to try and prevent. Fortunately, on this circuit breaker right here, we was able to catch it before it turned into full-blown arcing and make the repairs that were necessary. The third anomaly that I mentioned was Corona. And Corona is not the bad beer from Mexico, and that's a bad joke, but somebody at our office uses that. Corona is merely the ionization of air molecules due to stresses of the expanding and collapsing magnetic field on higher voltages in electrical systems. And what the ionization process does, it stretches the air surrounding that termination beyond its insulating point, because air is a very good insulator under normal conditions, but it doesn't stress it to its flashover point. There's a lot of what we call nuisance corona out there, meaning it's a naturally occurring thing. If anybody has listened to AM radio and they've driven under high-tension power lines and you hear the quote-unquote interference, that is nuisance corona. It's a natural thing because those higher voltages are stressing the air, the magnetic field is expanding and collapsing, and it agitates the air molecules. With infrared, you cannot see corona, whether it's nuisance or destructive. And the reason for that is the infrared cameras are designed to operate at wavelengths of either 3 to 5 or 8 to 12 micrometers in wavelength. It's light. Whereas the corona occurs in the ultraviolet part of the electromagnetic spectrum, meaning you need a different type of imager to visualize that. They do make cameras that can see corona. But if anybody owns an infrared camera and you thought that was expensive to purchase, try to buy a corona camera. But this screen capture right here shows what that would look like in the corona cam. It shows up as white dots around this insulator, for example, and that's where the ionization is taking place. To our ears, when we listen to it in the ultraprobe, it sounds like eggs frying on a griddle. It's just a steady buzzing sound that occurs. It makes it easy for us, when we're looking at it, if you know what you're looking for, to pick this out for nuisance or destructive corona, in that there's a lot of symmetry. So on the frequency domain, unlike the arcing and tracking where we only had a first couple of harmonic frequency faults there, we see that each 50 or 60 hertz frequency has a peak or a fault all the way across the spectrum, and it is loaded or very rich with frequency noise in between each one of those peaks. That's the first indicator that we're dealing with corona. In the time domain, we have a lot more symmetry here every other cycle, or half cycle, if you will. The broadband white noise is there, the excursions are very similar in amplitude, and they alter right between each other. So the abundant noise is a tip-off. The time domain and the symmetry is what is the clincher here when we're dealing with corona. If you look at it with respect to the sine wave, let me see, go back to this one, excuse me a minute. The destructive corona. I mentioned nuisance corona, and we just looked at the spectrums for that. Where destructive corona comes in, this naturally occurring process of ionization will ultimately release nitrates into the air. And when those nitrates mix with the moisture in the air, it forms a nitric acid. And nitric acid degrades and destroys electrical insulators. When this destruction occurs, you begin to have discharges of electricity along those insulators, i.e. tracking. And when those additional elements are superimposed on the naturally occurring corona, you get a different type of spectrum, which can be seen here. And the key thing is we begin to lose in the frequency analysis those 60 hertz fault frequencies we saw with the nuisance corona. They begin to disappear or get masked due to the discharges that are occurring now at non-uniform times on the sine wave. So we're back to what looks like tracking. And if we review that as far as what to expect, we have the first couple 60 hertz or 50 hertz harmonics rich in frequency content. That can clearly be seen here on the left. The difference on the right in the time domain is there is a lot of symmetry in the amplitude and spacing of the excursions that occur on top of the broadband white noise, whereas tracking in its purest form had the variations in the amplitude. So these are a couple of the things I pick out when I'm dealing with systems over 1,000 volts and I believe destructive corona is taking place. So that's what it's pointing out here. Very similar spectrums to tracking. That makes sense because now we have discharges on insulators, and that's occurring on top of the corona, which masks the fault frequencies, but we get greater symmetry in the time domain, as can be seen on the right-hand side here. Looking at it from the sine wave, when corona occurs, nuisance corona, the ionization takes place at the peak of the positive half cycle, which is why you are going to see there's a lot of symmetry here, or timing, if you will, every 16 milliseconds, and that gives us the rich 60 hertz fault frequencies and noise content, as well as the symmetry in the time domain when the excursions occur. It's a very uniform event, and it's easy to pick out if you know what you are looking for. Corona can be confused with some other issues that I'll talk about here in a moment. But one example of destructive corona that was found, and bringing up something maybe from your level 1 classes that you remember called sonic deflection. This picture right here was from Milwaukee in a mall complex that had twin towers on either side of the mall with a redundant loop feeder, 4160 volts. And this junction box was in one of the towers, and as you can see, there's two cables there. The left cable was an original one that was installed, I believe, 32 years prior. The right one had been replaced 7 years ago with a shielded cable. As we went into this room, we were doing a safety scan with the ultra probe, and we heard something. And through the gross define technique, using the sensitivity to isolate down where this emission was coming from, we came to this junction box. And right on the jacket of the front cable there, what was analyzed was the destructive corona that was taking place in between the semiconductor material and the outer jacket. So that was breaking down, and ultimately that cable will fail. And if it does in this particular setup, it's not going to be limited to just that particular cable. It'll probably blow out the other cable, and now the loop feeder is opened up. So we can see that pretty easily utilizing those techniques that I just referred to. The consideration with electrical is vibration and looseness. And depending on what we're looking at, in particular with transformers, we have a lot of cores, supports, hardware, wedges, nameplates, and things like that react very interestingly with magnetic fields. And that's what we have in transformers, is a concentrated magnetic field. And that'll produce ultrasound. Doesn't always mean it's a problem. And if we look at a typical spectrum right here with a transformer, we can see it looks very similar to corona on the frequency domain. And what I mean by that is we have each 60 hertz harmonic here. However, what is missing that was in the corona spectrum is the noise content, or frequency noise in between these peaks, is nearly non-existent. That's an indicator there that we're not dealing with corona. And if you look at the time domain on the right-hand side, you can see very uniform in the broadband white noise, the excursions, the spacing, and the amplitude. That's very typical of a properly functioning transformer there. Now, when you have problems within transformers, there's certain things you can look out for. You don't want to confuse corona with the vibration I just showed you. Remember that corona is rich with frequency content, whereas if it is 50 or 60 cycle hum or any type of vibration, that noise content will be absent. I had a technician from London send me a recording that produced this spectrum right here. And it sounded very different than some of the things we had heard, but the spectrum, as you see, looks similar to what I showed you on a properly functioning transformer. But there was one distinct difference on this particular transformer that I wanted to call attention to. And in the proceedings, I said, can you point this out to me? But the reality is the additional component exists with a 25 hertz fault frequency. And what I'll say about that particular frequency, number one, it is below the line operating frequency. Over in the United Kingdom, the power systems operate at 50 hertz. If you have a true electrical anomaly, whether it's 50 or 60 hertz, and you see a fault frequency like this that is below your operating frequency, it immediately rules out anything electrical. It's impossible to have a frequency like that on the spectrum if it's an electrical issue. This indicated a mechanical type problem, and what it ended up being was a nameplate where a rivet had come loose on the transformer and was vibrating, and it produced this spectrum. So it won't be electrical in nature if your fault frequencies are below your line operating frequency. That's a lot on the overview about how we're using the UltraProbe with electrical preventive maintenance, and believe me, the field is wide open. But the reality, to summarize all this, we believe ultrasound has proven to be an extremely critical augment to our maintenance program, and it should to anybody's. In particular with electrical equipment, you always have limitations with line of sight. Infrared is a great technology, but if you rely solely on an infrared camera for your maintenance program, you're not seeing the whole picture, or more specifically, hearing the whole picture. The more comprehensive our assessments are on the equipment, it allows us greater control over budgets and planning, and lets us be more effective in our efforts. The earlier we detect these anomalies and monitor them and come up with a course of action, the less expensive it is in the long run. And the biggest thing from our standpoint when it comes to the UltraProbe, it all started out with safety. Everything else is a moot point if you cannot keep your personnel safe. And before we take the first panel screw out of any piece of equipment, we're doing an ultrasonic safety scan. And the reason for that is you cannot put a price on human life. And we need our resources, and that's the most important resource as far as we're concerned. So summarizing that, the unheard really does have dire consequences if you do not find that early enough. And I would close simply by saying use every possible tool that you have at your disposal to maximize your effectiveness and your efforts on your maintenance program. And Gary, I think that that's a good place where I can turn it over to you.
Thanks, Joe. I'll take that back from you here. Let me get back up on here where I'll take back the control of the screen from Joe here. And as we said here, if you have any questions, keep them coming. You can always get us to them here at UE Systems, or you can get them to Joe at TEGG at TEGG.com. We want to really thank Joe and the TEGG network for doing this for us today. For those of you who don't know, TEGG has this worldwide network of people out there that provide a variety of testing and repair of electrical distribution. They actually offer services. They do inspections by these licensed electricians. They do infrared thermography. They'll do the voltage and current analysis, power quality. They'll use the ultrasonic along with that, all kinds of documentation. We hear a lot of good things about them from our customers in the field, so we really we enjoy being associated with them. For those of you who are familiar with it or not familiar with it, the unit that they use is the UltraProbe 10,000, and actually TEGG has done an awful lot on that with this NFPA 70E training. You'd have to contact Joe on what kind of services they offer with that, but I know they've done an awful lot of electrical inspector safety type training over the course of the years. Other opportunities that you have from UE Systems as well, along lines with our learning opportunities, we are doing some very specific compressed air inspector courses at different places around the country and the world. We got one coming up here in Canada as well. Just want to throw that up there for you, the dates that those are coming up. Those are just one-day courses. We're teaching people about energy efficiency. And we do other types of training things. We'll teach people very specific steam trap testing methods. We will teach people electrical inspection, bearing inspections. We do these full level 1 courses and level 2 courses at different places around the country, around the world. You can just come up to uesystems.com and keep track of us there. Our next webinar here in STEAM, in September, we're going to do one very specific on how to test steam traps with ultrasound and with other methods as well, with infrared. And I think with that, I'll let you guys go. If you have any questions for us, you can always reach us at info@uesystems.com. Joe, I really want to thank you for taking your time out. I know you're a busy guy, but we really appreciate that. For those of you that want to share this with other people, we'll put this up on our website where you can come view it at a later date. With that, for those questions that I did not get to on here, we will get back to you and see what we'll do. It'll take us about a day to get this up, and then we'll have it up on our website, and we'll send you the link for that. Thank you all for joining us today.
And thank you, Gary. I appreciate the opportunity, and be happy to help in any way I can.